Get going. Good morning, everybody. Welcome to another wonderful morning of Chem 1211 with your host, me, Dr. White. Now, on Thursday and Friday, I made a mistake. Yes, Dr. White makes mistakes, and I will correct that in a second. Uh, and I'll explain why. I actually took it out of the video for Friday, I think. But, anyways, that was with a balancing chemical equation. All right, heads up. Uh, I'll put out an email, but I'm going to have an amnesty program. Everybody has until Sunday noon to hand in any previous labs. After that, 2 days you haven't handed it in, you get a zero. It's as simple as that. Uh, and most of you are handing in your labs. Also, with the labs, I've come to gotten into how should I say a scheme of things. I graded over the weekend, and then on Tuesday I'll upload your grades to Blackboard. So I'll send out an email. If you haven't gotten a lab in, get it in by Sunday. That's the latest. If you don't have it, because you can't download it anymore, email me, I'll send you a copy. But labs are easy, 10 points, easy as they're not like it takes 5 hours each lab. No, it doesn't. So, all right, let's get to work and let me show you my mistake and how I found it. One of the things I don't like doing is if I look at a chemical equation, especially inorganic. Organic, I'm a organic chemist. I can see a mistake easily. Inorganic, sometimes I think it's wrong, but I'm not sure. I hate to go changing things uh, left and right. So I waited and I looked and I saw where the mistake was. And let me show you the following chemical equation. And the question is balances. And when I did it last week, I had mistakenly written this down as a 2, not a 3, which is why I couldn't balance it. But anyways, I'm going to let you try it first. Remember my advice. Leave oxygen and hydrogen last. And I messed up again. Ah, there we go. Now it's correct. So go ahead and balance it, and then I'll do it. I'll get you to work early in the morning on Monday. Well, not that early. And if you look on YouTube, you'll see I'm caught up to date with my videos, or actually for your videos. Oh, for those who are wondering, when I order, usually it's about twice a year from the Republic of Tea, I'll put in about $120, $150 order, but it lasts me a half a year or more, sometimes depending on my tea drinking. And Zoom meetings. And when I'm in my office more, which I am now, since we're not face to face, I'm drinking a lot more tea. I've had to cut back. And let's try the poll once more. Give a few more people a minute or so more. All right. It looks like everybody's done, but before I do this, and I have to make you wait, I just thought of something I forgot to tell you. Oh no. All right, listen up. It looks like our breakout room experiment is going well. And I thought, how can I expand it to help you? And I came up with the following idea, which we'll see how well it works. And that is, I have two Zoom accounts, one for COD, the other for Elgin Community College, that the college paid for. You don't have that. Or maybe you do and you have to pay your own Zoom account. And therefore, here's a special public service I, Dr. White, will be doing. That is on Monday and Wednesday nights during my office hour. I will set up breakout rooms. And if you want to meet with other your colleagues in 1211, just show up and say, could you put me in a breakout room with so and so? And the answer is yeah. Doesn't cost me anything. I'm still there for an hour and 15 minutes. If you want to be in a breakout room with some of your colleagues, discuss whatever, uh, I'll set it up and let you go and to the breakout room. And I look at it this way, it's a way of fostering interaction between all of you. And if you want, I'll stop by too, but I'll really probably won't because I'll be waiting for people in the regular Zoom meeting part of it for anybody who shows up. And so I'll say it again, starting tonight on Monday and Wednesday nights, if any of you want to get together with your other classmates, I'll set up a Zoom breakout meeting room and you guys can go in there. I'll put you in there and you can talk to each other. And with that, let's do the balanced chemical equation. All right, how do you balance it? Well, Dr. White's advice, which I follow my own advice most of the time, is, especially for balanced chemical equations, is leave hydrogen, oxygen last. So, aluminum, I have two aluminum. How do I get two there? I now have two aluminum. Now, carbon. I have three carbon. How do I get, well, here's the only place carbon is. I'll put a three there. I now have three carbon. Oxygen, leave to last, hydrogen, leave to last, phosphorus. I have one here, but 2 times 1 is 2 phosphorus. So how do I get this to 2? I put a 2 in front. And now all I have left is oxygen, hydrogen. And how do I do that? Well, let's take a look at this. I have, let's do oxygen. 3 times 9. 3 times 3 times 3 is 9. My brain's getting ahead of my mouth's getting ahead of my brain or vice versa, then 2 times 4 is 8, and that equals 17 oxygen. That. And now, if I look on here, I have 2 times 4 is 8 oxygen, plus 3 times 2 is 6 oxygen, and plus 1 is 15. Now I want to get to 17. And how do you do that? Once you've done a coefficient like this for a non-hydrogen or carb or oxygen, you don't want to change it. Oh, look, in front of water, there's a 1 there, but I can change that. I have 14, I want to get to 17. 17 minus 14 equals 3. So if I put a 3 there, I have my 17 oxygen. And what's left? Hydrogen. 2 times 3 is 6 hydrogen. 3 times 2 is 6 hydrogen. Now, before I leave on to the next problem, what I was doing, I'll check 2 aluminum, 2 aluminum, 2 phosphorus, 2 phosphorus, 3 carbon, 3 carbon, 17 oxygen, 17 oxygen. Ooh, home stretch. 6 hydrogen, 6 hydrogen. Success. Victory is ours. And that's how you balance chemical equations. Now, this Thursday, I'm going to do problem set for chapter 6, and I'm also going to throw in chapter 7 problem set, which is the balanced chemical equations problem set. Don't forget the lab is due also balanced chemical equations this Thursday or Friday. And when I say Thursday, I mean Thursday and Friday, not or. And that's how you balance chemical equations. Remember, it's a secret, but on test 4, there's going to be probably 3 or 4 12 points on the final. There'll be 12 or 14 or 15 points. I haven't written the final yet. Every semester I write all new tests and final because I let you keep it. Even if we were face to face, you get to keep my test. All right, let's move on. And let's talk about, and I'll never ask on a test, but conservation of mass. And there's the law of conservation of mass in any chemical equation. The total amount of matter in the reactants is equal to the total amount, the dreaded T virus got me, total amount of matter in the products. Now, how do we use that? We use that for calculating moles using mole factor in a chemical equation or calculation. Let's look at the following balanced chemical equation. And if we notice 4 hydrogen, 4, 2 oxygen, 2 oxygen, it's balanced. Now, the coefficients mean something. Here, the coefficient of hydrogen is 2. When there's no coefficient, it's a 1. We just don't write it. And here, the coefficient is 2. Now, what do those coefficients mean? Well, I'm about to tell you probably one of the most powerful things and teach you I know in all chemistry. I'll say that again. I'm about to teach you one of the most powerful concepts in all of chemistry. What is that? And that is the coefficients in a balanced chemical equation give the numerical relationship among formula units, otherwise known as molecules, or elements consumed or produced in a chemical reaction. Another way of saying that is, and I'll never ask that on a test, but I'll expect you to know how to use it, is the coefficients in an equation give the fixed molar ratios between substances consumed and, or it should be and products or consumed or produced in a chemical equation. That really should be an and. But anyways, let's go back and look at this chemical equation. The coefficients in a balanced chemical equation give you molar relationships between the reactants and products. What does that mean? First of all, in this balanced, and it has to be balanced, chemical equation, I now know 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. I'll say that again. 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. And because of that, I can set up relationships. For every 2 moles of hydrogen, I need 1 mole of oxygen. And I can do the reverse. For every 1 mole of oxygen, I need 2 moles of hydrogen. I can also write relationships. For every 2 moles of hydrogen, I make 2 moles of water. And I can also, and these are not equal, these are separate relationships. I can also say for every 2 moles of water, I need 2 moles of hydrogen. And finally, the last relationship between oxygen and water, for every 1 mole of oxygen, I make 2 moles of water. And for every 2 moles of water I make, I need 1 mole of oxygen. And this is one of the most powerful of all things I personally know in chemistry. Why? Because when you make things like this plastic bottle or the soap you hopefully used in the last 24 hours, those are made by chemical equations in chemical plants, first in a research lab. And I've done all that in various areas, not the plastic bottle, but soaps and other things I've worked in industry. How do you know how much do you put together? You use the mole-mole relationship. So anything you buy that has a chemical used to make that concept, the mole-mole relationship of a balanced chemical equation, help chemists like me determine how much of each starting material or how much product we make. And that's quite powerful. Let's look how we use it, or you could use it. And let's look at the following. Tonight I'll be taking writing lessons. That's better. For these problems, I'm always going to have to give you a balanced chemical equation. When I was a student, these type of problems, the teacher would have us, instructor, you got to balance it first and then do the problem. That's mean. So I don't do that. All right, let's look at the following problem. How many moles of oxygen are needed to make 1.57 moles of water? And let me just, I haven't done this all morning, but thumbs up, people. Can you see the problem? Thank you. All right, so how do you do this? Good question. Well, first of all, as you know, what am I trying to find? Moles of water. What am I given? 1.57 moles of moles of oxygen I'm trying to find, and I'm given 1.57 moles of water. Well, this is the only number I have to start with. And how do I proceed? Well, it's time again to use your good buddy, your good friend, unit analysis. I love that. And if I had a ratio multiplying this number, moles of water, what answer do I want? Moles of oxygen. And now using unit analysis, whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of unit-wise goes underneath. And oh no, where do I get these numbers? You look at this balanced chemical equation. Tells you 2 moles of hydrogen react with 1 mole of oxygen when there's no number in front, it's 1, to make 2 moles of water. And so if I want moles, O2 on top, moles of water underneath, for every 1 mole of oxygen, I make 2 moles of water. Now, listen carefully. The coefficients of a balanced chemical equation are exact numbers, and they never play a role in determining significant figures. I will say that again. The coefficients of a chemical equation are exact numbers, and they never play a role in determining the number of significant figures. So if I'm multiplying 1.57 times 1 divided by 2, the only number that's significant figures is this, 3, 1.57. And that tells me how many significant figures my answer should be. So now it's time to go to Dr. White's calculator. And here's the number I get, and to 3 significant figures. That was an easy, good pick. That'd be 0.785. So I need to react 0.785 moles of oxygen to make 1.57 with the hydrogen, with the water, to make this amount of water. Let's go through what I did again. First, I determined, what am I trying to find? Moles of oxygen. What am I given? Moles of water. This is the only thing I have to start with. What units do I want to get to? Moles of oxygen. I use my good buddy, my good friend, unit analysis. Moles of oxygen go on top because I wanted my final answer. Moles of water go underneath. Why? Because anything divided by itself equals the number 1. It cancels out. So this would have canceled out. And where do I get these numbers that go in here? From the balanced chemical equation. 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. And that's how you do it. Oh, I better share. All right, let me decode this. How many moles of water will I make if I react 1.783 moles of hydrogen with an excess of oxygen? Now, let me explain something that I could have put in the previous. Whenever you see an excess of something in a chemical reaction being used, ignore it, because that only tells you you got all of that chemical to react with anything that chemical will react with, and you can just ignore it. So I'll let you try this one. Don't forget to use your good buddy, your good friend, unit analysis. And for those of you who didn't notice, I'm having a good hair day. It's still there. Any day is still there is a good hair day for Dr. White. Just think, I get paid to provide you with awful humor. Oh, Dr. White's happy. I see all the students out there in student land working on mole problems. Life is good. I really mean that too. All right, most of you are done, so I'm going to move forward. I'll give you another 15.2 seconds. Go. I'm watching my clock that doesn't tick or talk. It's electric, digital too. All right, time's up. Gave you an extra second or two. Let's take a look. How do you solve this? Well, the first thing you do is, what are we trying to find? And the answer is moles of water. What are we given? And that answer is 1.783 moles of hydrogen. And we're also given a balanced chemical equation. So now it's time to use our good buddy, our good friend, unit analysis. And if I had this and I had some ratio, I can multiply my number 1.783 moles of hydrogen. What units do I want my answer to be? Well, we figured that out. Moles of water. And now we'll use our good buddy, our good friend, unit analysis. Whatever I'm trying to get to, the units go on top. Whatever I'm trying to get rid of, the units go underneath that ratio. Let me put that in. And where do I get a ratio of moles of water to moles of hydrogen? From the balanced chemical equation. And if you look at this, remember the coefficients tell you 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. So I know for every 2 moles of water, how many moles of hydrogen do I need? 2. And don't forget, these are exact numbers. And before I pick up my calculator, remember moles of hydrogen divided by moles of hydrogen, anything divided by itself equals the number 1 because it cancels out. I'm left with the correct units. And now I'm going to go to my calculator. No, I'm not. 2 divided by 2 is 1. So the answer here is 1.783. Now, remember, since these are exact numbers, you don't use those determining significant figures. This has 4. Your answer better have 4. Oh, this is fun. I got to do another one.
Hey,
Yeah,
Dr. White.
I hear a question. Go for
Yeah,
it.
you said the moles, you got them from the balance, correct?
The what?
The two
The
from the,
ratio?
yeah,
Let
you
me
got
do
them
it
from the
again.
balance, correct?
It has to be balanced, which is why I spend a lot of time balancing. But good news on these type of problems, I'll always give you a balanced chemical equation. Always. If I don't, you can't do the problem.
So in this one, it's just kind of like throws you off because it indicates the O2. Um,
Right.
right.
Here,
Okay.
let's take a look. Let's go through it again. A balanced chemical equation gives you molar ratios. And this one right here tells me 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. So I have the relationship for every 2 moles of hydrogen, I make 2 moles of water. There's other ones, but that's the one I need right here for this problem. Does that help?
Yeah, it was throwing me off. Okay. Okay, I see.
Don't forget, there's no such thing as a dumb question. Ooh, that reminds me. I think I might have mentioned it once or twice before. If I say I'll bet, I already know I've won. And I will bet that if you ask a question about anything in this class, a good majority, or maybe not a majority, but a good number of your colleagues will have the same or similar question. So always ask questions because not only are you helping yourself out, but you're helping your colleagues out. And I found that to be true in teaching. One student asks a question, a lot of others have the similar question. Let's do another one. And why don't you try this one for our fun and enjoyment on this beautiful sunny morning? And I'll read it so you know what I wrote, decode it. How many moles chlorine, Cl2, are needed to make 4.76 times 10 to the third moles of sodium chloride? Where'd that extra 2 come in? Oh no, the dreaded 2 virus got me. Corrected. Ready, set, go. Actually, this is not a competition. You're doing really high level chemistry now. So take your time, relax. If you're not getting it at first, we'll do more practice problems. Trust me, I'm a doctor. Does that work? How about trust me, I'm a chemist? Did that work? How about put it all together? Trust me, I'm a doctor of chemistry. Did that work? Those who finished early, please be patient. I try and give everybody time to finish. All right, looks like everybody's done, so I better get to work. And the question is, how do you solve this problem so you get your 5 points? See, Dr. White was a student once too. And if you do that, I get what I want. You learn how to do this. Well, first of all, what are we being asked to find? Moles of chlorine gas, Cl2. What are we given? 4.76 times 10 to the third sodium chloride. And as I've told you, if I'm in a restaurant with other chemists, or one of us will all ask, please pass the NaCl. But anyways, now, how do you proceed? Use your good buddy, your good friend, unit analysis. This is the only number I have to work with. If I had a ratio that I could convert this to my answer, what units do I want my answer in? Well, the answer to that is moles of chlorine. And how do you use unit analysis? Your good buddy, your good friend, whatever you're trying to get to goes on top. Whatever you're trying to get rid of goes underneath. And now I'll write those in first. That's NaCl. Hold on. And where do we get these numbers? From the balanced chemical equation. Remember, the coefficients tell us molar amounts or relationships. Every 2 moles of sodium react when there's no number there, it's the number 1 mole of chlorine to make 2 moles of sodium chloride. I'll say it again. For every 2 moles of sodium, I react 1 mole of chlorine, Cl2, to make 2 moles of sodium chloride. So if I know for every 1 mole of chlorine, how many moles of sodium chloride do I make? 2. And now before I pick up my calculator, I'll say, do my units cancel out so I get the right answer? And the answer is moles of sodium chloride divided by moles of sodium chloride. Remember, anything divided by itself equals the number 1, cancels out. And yes, I get what I want. And now I'll go to my calculator, but let me remind you, in this reaction, or not reaction, this calculation, 1 and the number 2 come from a balanced chemical equation. and those are exact numbers, and therefore three significant figure, my answer should have three significant figures. And now I can go to my calculator. Let's come over to this side because wrong side. And this is the number. I'm on a winning streak. Round this out to three significant figures. By the way, I just picked numbers at random. And for this to happen twice in a row, I'm going to play the lotto tonight. Not really. And the answer is 2.38 to three significant figures times 10 to the third. And that's our answer. And that's how you do it. Let's go through this once more real quick. We found out what are we trying to find. We look at what are we given. This is the only number we're given. We start with this. We use the unit analysis. What units do I want my answer to be? Moles of CO2, because we figured it right here. Whenever I'm trying to get to, the units go on top of a ratio. Whatever I'm trying to get rid of, the units go below. And where do I get these numbers? From the balanced chemical equation, which are given up here. 2 moles of sodium react with 1 mole of chlorine to make 2 moles of sodium chloride. 1 mole of chlorine makes 2 moles of sodium chloride. And that's how you do it. And oh no, time flies when you're having fun with balanced chemical equations and mole-mole relationships. It's time for our 5-minute break. I'll see you in 5 minutes at 10:55. Dr. White's going to go stretch. Time to start. Everybody back? All right, let's get back to what we're talking about. And that is in a balanced chemical equation, the coefficients, the number in front of an element or molecule in a balanced chemical equation gives you molar relationships. Example, in the problem we just did, 2 moles of sodium react with 1 mole of chlorine to make 2 moles of sodium chloride. And I just have to balance this in my head. Let's see, 3 carbon, 3 carbon. You won't have to do this 8 hydrogen, 10 oxygen, 3 plus 4. It's a balanced chemical equation. By the way, this is propane. That's the empirical formula. Organic chemists would write the structural formula, which is this. That's also propane. And that's the stuff doesn't sound professional. That's the substance that's in the white tanks that you buy for your barbecue. And when you react with oxygen, a little spark, you burn it. What I don't put down here is you get heat. It's called combustion. I'll teach that later. And you make carbon dioxide and water. So let's do the following. Oops. Nope, it's still on that one. And let me decode this for you. If I react 4.709 moles of propane, C3H8, with an excess of oxygen, then how much carbon dioxide will I make? I see a question, so before we let me read it, let me rewrite this because one of you, I'll rewrite it again on top. I'll push harder. Is that better? And so I'm going to let you try this first because I'm in a good mood and I'm going to share the fun. Your turn. Get to work. That's not polite. Get to work. Could you please work on this problem and get to work? And I notice where I say how much, and I probably for this type of problem should have gone, this is better. How many moles? Sorry about that. I assumed you knew much means moles, but that's not polite. Bad, Dr. White. Shame on me. Oh no, I made a mistake. I gotta go home. Wait, I am home. All right, before we move on, which we will do this problem, got a question for all of you, and that is, how many of you like the polling better than thumbs up? Give me a thumbs up now. How many like my thumbs up better than polling? It's about 50-50. I'll do some other. One of the disadvantages of being on Zoom is when I'm in a classroom, I can just look around and look in the classroom. And I usually tell the students when you're done, look up and smile. I have a lot of smiling faces in my classroom. I'll do both. I'll alternate. Yeah, hopefully I've given you enough time. I see. Yeah, both are equal. All right, let's do this. And the question is, if I react 4.709 moles of propane, C3H8, with an excess of oxygen, then how many moles of CO2 will I produce? And now what do? You say, what am I trying to find unit-wise? And the answer is how many moles of carbon dioxide. By the way, next time you burp, Most of your burp is CO2. And what am I given? 4.709 moles of propane, C3H8. And now this is the only number I have to work with. Oh, one other thing you're given is the balanced chemical equation. But let's continue here. This is all I have to work with. If I have some ratio I can multiply this by, what would be the units I want to get my answer? Well, we took the time to figure that out. That's moles of CO2, carbon dioxide. And now I'll use my good buddy, my good friend, unit analysis, whatever I'm trying to get to, the units go on top of this ratio. Whatever I'm trying to get rid of, the units go underneath. I can do that now. And now the question is, where do I get these numbers? From the balanced chemical equation, propane. When there's no coefficient in front, it's the number one. So 1 mole of propane makes how many moles of CO2? And the answer is 3. So for every 1 mole of propane, I make 3 moles of carbon dioxide. Remember, these are exact numbers. So they play no role in determining how many significant figures your answer is. Notice this is multiplication and division, and therefore the number of significant figures you get should be the same as the number you're multiplying or dividing with the lowest significant figures. Well, this is the only number with significant figures. It has 4 significant figures, and therefore our answer should have 4 significant figures. Now, before I pick up my calculator, I'm going to see, do I get the right units if I just do the math without the numbers? Moles times moles of propane times moles of CO2 divided by moles of propane. Anything divided by itself equals the number 1. And therefore, this cancels out. I'm left with moles of CO2, carbon dioxide, which is what I want. So now I can pick up my calculator and see what answer I get. Now, I could have also done this in scientific notation, which most of you probably have your calculator in. And which one is the right answer? Either one. Now, rounding these off to 4 significant figures, I keep on the scientific notation, keep the 1, keep the 4, keep the 1, keep the 2, use the 7 to round off. That's 5 or greater. That gets dropped, and the 2 becomes a 3 times 10 to the first. And then, can you see my? I'll get back to you in a second on that, Gabriella. And on this side, this rounds off to 14.13, which is the same number. And now, let's go back here. And this would be either 14.13 or 1.413 times 10 to the first. Let me rewrite it underneath. 14.13 moles CO2 or 1.413 times 10 to the first moles of CO2. And that's how you do it. Now, one of your colleagues had a good question, which is confusing at first, is how do you know what to multiply and divide? Well, you use unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of, the units like here, go underneath. And that tells you, once you put in the numbers, what you get from 1 mole of propane and 3 moles of CO2. And that's how you know what to multiply and divide, because this will cancel out and this will leave me with the right units. Now, if you're having trouble with that, I'd highly recommend stop by my office hour tonight or Wednesday, or if you can't, if you have lab on Thursday, I'll stick around, or after lab, or if you have lab on Friday, I'll stick around. Don't tell anybody I'm being nice. Shh. And does that help your question?
Yeah, Doctor, it was more of the lines of when you're getting the final answer, because I saw that I think it's either dividing the ratios or you multiply them, and I'm not quite sure how.
All right, well, you just do the number here. All right, let's quick little math. What does this equal? Equals A, and we multiply this times that, B, and we're dividing this by C. Does that help you?
Yeah, it does. Thank you.
You're welcome, and that's a good question, because in Dr. White's class, all questions are good questions. And this way, you and anybody else who have that sort of concern or question will now do it right on the test, which I hate to say this, but Dr. White's very selfish, because if you get it right on the test, I feel good and makes me feel good. So that's why I teach this stuff, just to make me feel good, also to help you learn it, which also makes me feel good. All right. Now, if we had been working in the lab, which unfortunately we're not, you would have seen in our lab at COD, we have balances and we have analytical, which are very accurate. And we have the kind you just put it on top. Those are called top loaders. Every balance in our lab weighs or gives units of grams. I think the top loaders you can change to ounces and pounds, but those are still weights. I have never seen in my life a balance that will give you moles. If I have a certain amount of water in a beaker, they'll tell me how many grams, but I don't know how many moles. Well, what does that mean? That means the following. If I'm doing the type of question in real world, like in a chemical plant, ooh, hold on. I have a little surprise for you in a little while. I can't tell you, it's a surprise. But anyways, what does that mean? Well, we did our practice times. Let's look at the following problem. And the question is, given a balanced chemical equation, how many grams, G is grams, of oxygen are needed to make 15.6 grams of water? Well, how do you do that? Well, Dr. White's taught me how to do this. I'm going to find out, first of all, what am I being asked to find? Grams of O2. What am I given? 15.6 grams of water. Therefore, if I can convert this in one step, the only thing I have to start is grams of water. And what units do I want my answer to be? Grams of O2. And Dr. White has taught me that using unit analysis, whatever units I want, go on top, and whatever units I'm trying to get rid of, go underneath. And now I'll put grams of O2, and here I'll have grams of water. And then the question is, where do I get these numbers? And the answer is I'm stuck. There's no way to find these numbers. There's no relationship, even from here, of grams of oxygen to grams of water. It does not exist. I'm stuck. What do I do? Oh no. Relax. You use mass calculations for a reaction. Finding moles or mass, actually mass, of a substance in a chemical reaction, you use the following 3 steps. Oh, the last one I forgot to put. This will be given to you in important information, test number 2 and the final. And how do you use this? When you're trying to find the mass of a substance, I really should take that out, in a chemical reaction, convert the mass of A to moles of A. You learned how to do that already. Convert the moles of A to moles of B. I just taught you that. And finally, convert the moles of B to mass of B. So let's look at what we have. But before I do that, one question you should always feel free to ask me, why am I learning this stuff? Well, the obvious answer is someone wanted you to learn chemistry and you want to get a good grade so you can get into a program or a school, and that's why you're learning it. But chemistry plays a role in our everyday life. Let me see if I can find something real quick. Show and tell time. Everybody see someone on the screen that looks familiar? It's me, Dr. White. Here I'm in a chemical plant. They just washed the floors. This is probably one of the cleanest chemical plants I ever been in. I worked for this company. It was called Borden Chemical. I'm in Louisville, Kentucky. This is a reactor behind me, not a nuclear, chemical reactor. It's a vessel you make chemical reactions, do chemical reactions in. This is huge. I'll show you all these pictures later on this semester. But in that reactor, I think that's either KRL reactor in the Rizal building. Different chemical companies name their reactors differently. That you do reactions with 160,000 pounds. You can tell I'm in a chemical plant because I have my hard hat on and I have safety shoes on that are steel toe. And I'll tell you the story later behind this picture later on. How do you determine how much of chemicals to put in here to make what you're trying to make? By the way, what we're making here was called a resin, which is a fancy name for a glue that holds different things together. What things are held together? Well, that company, which was Borden Chemical, they since changed their name to Hexion. make two types of resins mainly. One for what's called their forest product division, which holds pieces of wood together to make things like plywood for your home or into strand board and particle board. And also, when the salesman had a customer that would glue wood together, pieces of wood, to make your toilet seats. We cornered the market on resins for toilet seats. That salesmen get grief at salesmen's meetings, grief by bad jokes. I'll let you think of them. But anyways, the other division, which I work mainly with, held pieces of sand together to make what? Molds for foundries. What do they do? Well, our biggest customers were GM, Ford, and then back then when I worked for them, it was called Chrysler. Now it's Daimler Chrysler. And that would be used to make the molds to make things like a car engine. And Dr. White has some fond memories, at least after I've solved the problem they're having, being at the GM Saginaw foundry, which if you've ever been on COD campus, the Saginaw foundry is about 2-3 times bigger than our whole campus at COD. I've also been to the Ford Windsor plant where they make engines. In fact, both times I was at each one where they're making V8 engines for their cars. Awesome site. And I'll tell you more about that later in the year. So by using the following calculations I'm going to be teaching you, chemists can know how much of different chemicals to mix together to make products. Now, one more thing before we get moving. Everybody see the tank wagon on your screen? Just to give, these are standardized throughout the chemical industry and other things like gasoline, milk even. They hold 40,000 pounds, 5,000 gallons, period. They all do. And when that reactor you saw me in front of, its practical capacity, how much you normally put to make chemicals in there, would be 160,000 pounds or 4 of those. That's exciting. And let me show you now the calculations. So if we look at here, we say this is not going to work. Won't work. You need 3 steps. Which is why this is sometimes 10 or 15 points, because it's more work. All right, step 1. Oops. Step 1, whatever you're given in grams, and I'll call that grams of A, you convert to moles of A. So what are we given in grams? Water. So now for step 1, we have to go from grams of water to moles of water. And we have 15.6 grams of water. We use our good buddy, our good friend, unit analysis. We want to get the moles of water. And using unit analysis, whatever we're trying to get rid of goes on top, or get to goes on top. Whatever we're trying to get rid of goes underneath. And here we have moles Ah. One of these days, I'll figure out how to do the macros to change pen colors. I can do other things. I haven't figured that out yet. All right, you got, let me know when you got that. Unfortunately, this takes a lot of room. So on a whiteboard, I cover most of the front of a class. Let me know when you've copied that down. I'll assume you got it. And let's continue. Now, where do you get these numbers right here? In important information, 1 mole compound equals its molecular weight in grams, and the molecular weight in grams equals the sum of all atomic weights in grams. And what's the molecular weight of water? Because we need that, because 1 mole of water equals the molecular weight, and that's 2 hydrogen, 1 oxygen, and to use atomic weights, the 3 significant figures. For hydrogen, it's 101. For oxygen, it's 16. 2.02, 16.0. Add them up. You get the same number of significant figures as the number that has the lowest significant figures you're adding to the right of the decimal. That's 1. Here's 1's 2. Drop that. This is 18.0. So now, before I go to my calculator, I want to get to moles at the step 1. I want to get the moles of water. Do I get that? Notice grams of water divided by grams of water cancel out. So I do. And now I'm going to go to my calculator. And you can do this in scientific notation. I'm going to do it just regular. And this is a number, and it should be 3 significant figures. So I'll round it off, 0.867. The spreadsheet's going to pop some zeros in, ignore it. And now, something I need to talk about. And that is when you have multiple calculations, we're going to be doing 3 of them. Do you round off at each step or wait till the end? And did I lose some people? All right, we're going to be doing 3 calculations. We did step 1. We're going to do 2 more steps. Each one involves multiplication division. And when you get your final answer, do you round off at each step or do you round off at the very end? And the question is, which is right? Now, Dr. White is the philosophy. I round off at each step. And as I said, I've done calculations for large amounts of chemicals. We're talking my calculations. If I got it wrong, I've just destroyed close to $250,000 of chemicals. You do that, you get fired like that, quick. You don't do that. How did I make sure? Well, I do the calculation, let it sit a day or two, do it again, do it far enough in advance, and check the 2 numbers. They better be the same. Otherwise, I go back, where did I make a mistake? I didn't, never did, because I used to check that. But anyways, I'm round off at each step. Now, I know other chemists who say, no, wait until the end. So good news, Dr. White's not going to force you to do one or the other. What am I going to do? I'm going to have two possible answers on the test. And that is if you round off at each step or round off at the very end. Now, which is right? Both are. Now, a lot of times they're identical. Sometimes they're different. If they're different, that means there are two possible answers I will accept as being correct on the test. And that's because I'm not going to force you to do what I like to do, that is round off each step, because there's still an argument which is right, which is wrong. So I'm going to show you how I do that when I'm grading and doing the practice problems too. Now, I'm going to put down in my answer the round off at each step, and the same thing, and I think I do it both in the problem sets, but I will in the final show you the round off at the final. So step one, we've converted moles of A, grams of A to moles of A. And we have this number, which is not what we're trying to get to. So what do we need to do? Next, we need to do step number 2. Moles of A to moles of the answer we're trying to get. In this case, we now have moles of water, and we're trying to get to moles. What answer are we trying to get to? Oxygen. Well, grams, but not yet. We're going to go to moles of what we're trying to get to, O2. So I've just calculated moles of water. By the way, take a deep breath. I'm going to go through more of these on Thursday. These are challenging, but with a little practice, you'll get it. What am I trying to get to? Moles of O2. And now I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to, units go on top of this ratio. Whatever I'm trying to get rid of, go there. Moles of O2, moles of water. And where do I get these numbers? Where do I get the ratio of moles of one thing to moles of another? In our balanced chemical equation. And we're trying to get moles of oxygen, moles of water. And here, 1 mole of oxygen makes 2 moles of water. I'll say that again. 1 mole of oxygen makes 2 moles of water. So, and let me write it here. The balanced chemical equation tells me 1 mole, when there's no number, it's number 1. 1 mole of oxygen makes 2 moles of water. And now I'll use unit analysis to my units cancel out. Moles of water divided by moles of water. And now I know anything divided by itself equals the number 1, cancels out. I'm trying to get the moles of oxygen. This will get me there. And remember, the 1 and the 2 from the balanced chemical equation coefficients are exact numbers. So here, at this point, doing my way, I have 3 significant figures, and I'm going to divide by 2, multiply times 1, divide by 2. I'll go back to my spreadsheet. And here's how I do both ways. Now this number right here, I'm going to round off the 3 significant figures, and this would be 0.434. And this is how I do my calculations. So here's my second answer, and I'll write it 0.434. If you're not rounding off, this is where you're at in here, right here. And now I have moles of B. Am I done? No, I'm trying to get to grams of oxygen, but I have moles of oxygen. So it's now, let me move me over here. It's now time for step number 3. Moles of B, whatever we just calculated, to grams of B, which is what we're, why did I put a 2 there? Thinking of O2, my head's getting ahead of myself. And in this case, we have moles of O2, which we just calculated, and we want to go to moles, grams of O2. And we just calculated we have 0.434 moles O2, and we'll use our good buddy, our good friend, unit analysis. I want to get to grams of O2 because that's my final answer. And I'll use unit analysis. Whatever I'm trying to get to goes on top. Does this look familiar like we did this last week? And the answer is yes. Notice how I did incremental, teaching you different things with moles, and whatever I'm trying to get rid of goes underneath. And where do I get this? These numbers right here. I know that 1 mole of a compound, and this is an important information, test number 2. I used to make students memorize this, including the 3 steps that will be given to you. Important information, test number 2, and the final 2. Moles of a compound equals the molecular weight in gram of the compound, and the molecular weight in grams of a compound equals sum of the atomic weights. In gram of the compound. So for oxygen, I have 2 oxygens. Each oxygen to 3 significant figures is this number, 16.2. Remember, this is an exact number. We're doing a multiplication. 32.0 is the molecular weight of O2. Let me just do this. So I know for every 1 mole of oxygen, I have 32.0 grams of oxygen. And now before I pick up my calculator, do my units cancel out? Moles of oxygen divide moles of oxygen. Anything divided by itself equals the number 1. It cancels out. Therefore, am I left with what I want, grams of oxygen? And the answer is yes. By the way, this is 32.0. And this is 3 significant figures right here. I have 3, so my answer should have 3. Yes, Dr. Whiteson is right. So I'm going to take this number and divide it by 32.0. And I'll take this number and also divide it by 32.0. Now, both of these should be 3 significant figures, And if you notice, there's a difference. This one in column E, I round off 0.0135. This one 0.0136. And which is the correct answer on my test? Both. And that's how many grams of O2. Wait a second, did I divide? Yep, I should have multiplied. Sorry,
Yeah.
I caught it. Looked too small of a number.
Yeah. Okay. I wonder. I was like, what the-
And let me do this one.
Yeah.
And if we round this off to 3 significant, oh, it comes out the same. 3.9. Forget about the zeros. And this becomes, I'm 13.9, 13.9. Let's look and see if I did this right. Keep the 1, keep the 3, keep the 8. The next number to round off is, guess what? 5 or higher, drop that, increase that by 1. Same thing here, keep the 1, keep the 3, keep the 8. This is greater than 5 or greater, drop that, increase that. So the answer is 13.9 grams.
That'll be forever, Doc.
Who's ever got their mic on, please shut it off. $13.9. And there's our answer. Whew, that was a lot of work. Let's go through it again real quick because we're almost out of time, but we got time to go. All right. When you're trying to go from how many grams of a substance, in this case, oxygen, are needed to make 15.6 grams of water, and you're given a balanced chemical equation, you need 3 steps. All right, the question is, how do you know? Well, if you do it stepwise, each one, you look at the math, multiplication, division, you get the same number of significant figures as in your answer as the one that you're rounding up, that you multiply or divide that has the lowest. And either way, if you look at all the numbers you're given, not calculated, there are always 3 significant figures with that one. All right, let's go through this. I may go a minute more, but hang in there. You're welcome. Ah. All right, so whenever you have grams of something to grams of something else in a balanced chemical equation, you need to use the 3 steps. And the first step is convert mass of A to moles of A. Second step, moles of A to moles of B. This used the balanced chemical equation. We did that earlier today. And finally, moles of B to grams of B. And A is whatever you're given initially in grams. B is what you're trying to get to. If you notice, step 1, I converted the grams of water to moles of water. This is 3 significant figure, 3 here, exact number. Step 2, and just you learned today, how do you go from moles of one substance to another? Use the balanced chemical equation. 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. I have my moles of hydrogen, water, to go to moles of oxygen using an analysis. The numbers here come from the balanced chemical equation. And finally, I now have moles of oxygen. I want to go to grams of oxygen. I use 1 mole of a compound equals the molecular weight, and the molecular weight is the sum of atomic weights. and we've done this before, and this is the answer. And with that, I apologize for going 60 seconds late, but I did want to review that again. I'll see you on Wednesday. Don't forget, do the problems, practice problems. We'll do chapter 6 and 7 in lab on Thursday and Friday. Don't forget, hand in your lab. I'll send out an email about my amnesty program. You have until Sunday to get all your labs. If it's no longer a link, email them to me. Otherwise, you get a 0. With that, I'm going to say, gang gesund, be healthy. I'll see you on Wednesday.